In this lecture, we look at the kinetic energy of rotation. The kinetic energy of a rotating system is the sum of the kinetic energy of all the particles in the system. For a single particle, the kinetic energy is equal to 1/2 times the mass of the particle times the velocity of the particle squared. For many particles, the kinetic energy of the system of particles is equal to the sum of the individual kinetic energies, which is equal to the sum of 1/2 times the mass of a particle times the velocity of each particle squared. If we look at an object which consists of many particles, that is rotating, we see that all the particles on the object are rotating with the same angular velocity omega. But in general, they are at different distances from the axis of rotation. So if we try to write down the kinetic energy of the entire object, or rotational kinetic energy of the entire object, we have the sum of 1/2 m times the velocity of each particle squared. And we rewrite the velocity of each particle in terms of its angular velocity by multiplying omega times the distance from the axis. So we have 1/2 times the sum of the mass of a particle times the square of the distance from the axis times the angular velocity. It's convenient to group together the structure of the system in this equation, the parts due to the mass and the distance from the axis. So we rewrite this kinetic energy as 1/2 times the thing in the square brackets, which is the sum of the mass times the distance squared from the axis, times the angular velocity squared. We can call the object inside the square brackets the moment of inertia, and we symbolize it with the capital letter I. We'll talk more about the moment of inertia in our next lecture. Let's look at an example of the energy of a few rotating particles. There are 7 identical particles that are evenly spaced on a massless rod. The rod spins about the center particle. The total length of the rod is L, and the total mass of the system is m. What is the rotational kinetic energy? Well, we can start writing it down that the kinetic energy is equal to 1/2 times the sum over all the particles, where we've taken the total mass of the system and divided by 7 to get the mass of one particle. So the mass of one particle times its distance from the axis squared ends up in the sum in the square brackets times the angular velocity squared. Now let's think about the problem a little bit. The center particle is at 0 distance from the rotation axis, so its kinetic energy is 0, so we don't have to worry about that one. The particles to the left of the center particle have the same kinetic energy as those to the right of the center particle, so there's no need to calculate all of them. So in the end, we only need to calculate 3 energies and then double the result. So we're looking at those 3, which are at L divided by 6, and L divided by 3, and L divided by 2 away from the center axis. If we plug that in, there's the 2 for doubling, and then we have 1/2 omega squared times the mass of a single particle, m over 7, times the squares of the distances from the axis summed. So L over 6 squared plus L over 3 squared plus L over 2 squared. Perhaps surprisingly, this all simplifies rather nicely when you do the arithmetic, so that the kinetic energy ends up being 1/2 omega squared times the total mass m times L squared divided by 9. Again, we can rewrite this in the form of 1/2 I omega squared, where I is equal to 1/9 ml squared for this case.